So good morning to those in North and South America. Good afternoon to those in Europe and Africa. And if you're somewhere else, you should probably be asleep, and that's probably better use of your time than listening to me. So what I want to do this morning or this afternoon for you is I want to talk about arcs, rifts, and metallogeny. So it's a big, very general topic, and I'm going to touch on a number of different themes, things that have actually bothered me over the last many years. And I'm going to stray into turf that I'm not necessarily totally comfortable with, and so some of you will be shaking your head in frustration or whatever, or concern at some of the things I may say. But fortunately, because I can't see you, it's not going to bother me at all. You can do whatever you want. You can throw things at the monitor, and that's just totally fine. But really, the purpose of this talk is inspired largely by trying to understand iron oxide copper gold deposits. And that in part comes from the work that Irene Del Real did with me when at Cornell. And I think Irene and her students in Santiago are on this webinar, so that's very cool. And IOCGs are very difficult and still remain very confusing deposits. So why is my slide advancing? There we go. So what I'm going to do, I'm going to start talking about arcs and tectonics, and particularly some porphyry deposits, which are really in many ways the type deposit of arc settings. Then I'm going to go to rifts and again talk about some tectonics, magmatic sulfides, which are again typical of rift environments, and sediment-hosted copper, and a few other styles of mineralization. And then I'll move to iron oxide copper gold deposits, and really the question I'm trying to address is, where do they fit? Are they related to arcs? Are they related to rifts? Or is this some kind of transition between the two? So we'll start with arcs. And as I mentioned, porphyry, copper, plus or minus molybdenum, gold are kind of the type deposits of arc environments. But there are many other related deposits that go with porphyries. Porphyries are complex systems, and so we got a variety of different other styles of mineralization associated with them. Then we have gold deposits. And there are gold deposits associated with porphyries, particularly high-end intermediate sulfidation state ones, but there are separate and distinct gold deposits, the orogenic class being probably the most important, but also intrusion-related, low sulfidation epithermal, etc., other styles of gold mineralization. Then in arcs, both internal and in back arc environments, we have VMS, or for the Australians who should not be on this call, VHMS deposits, which in many cases in ancient arcs are part of the accreted terranes that have been amalgamated during collision. And then finally, in arcs, in some cases, we have iron oxide copper gold and the so-called iron oxide apatite deposits, and occasionally magmatic Ni-Cu-PGE deposits, although they are not regarded, this is not regarded as the main environment for these types of deposits. I'd note that in BC currently, there are a couple of projects in arc terranes for Ni-Cu-PGE. So the porphyry deposits, if we start with porphyry deposits, because they, again, are the big deal for the arcs, we have a pretty well understood environmental setting geological model for porphyry deposits that relates them to subduction zones. And this is an old model diagram from Polly and Schmidt showing the concept of dehydration of the slab and melting above the slab, the subduction zone area. And then a lot of complicated processes that happen at mid-crustal levels of melting, mixing, assimilation, fractionation, and so on, that give us the typical wet, oxidized arc magma suite, which we are characterized as being the source of the metals and the fluids that generate porphyry coppers once these apophyses of these deeper magma chambers are placed into high-level structural environments. And as a result, if you look at the little diagram on the left, you can see where the porphyry deposits occur. They obviously are in the arcs on the western side of North and South America and through the Southeast Asia, Southwest Pacific, and then caught up in ancient arc terranes that have been trapped during collision through Central Asia, through the Tethyan, and so on. So they are a fundamental part of arc type environments. However, not all arcs are created equal. And Dick Silito pointed this out in his paper in 2012, where he looked at the endowment of different arc segments around the Circum-Pacific. And so if you go to the bottom right-hand corner, and I'll try and use the cursor here occasionally just to help you, down over here, you can see that Chile-Peru is the dominant in terms of metal endowment, in terms of copper within the arcs, but we have substantial amounts up in here in Arizona, and then over in Papua New Guinea and New Guinea. And so there are other significant areas, but there are equally large segments of arcs which have essentially no porphyry copper endowment associated with them. So that's an interesting fact. And of course, lots of people have suggested reasons for what makes the endowment, say in Peru, Chile, versus the less endowed parts of some of these terranes. So one of the things that has been considered, if you go to the central part of the Chilean copper belt, or actually the southern part, really, the central part of Chile, to the big Miocene deposits of Los Pelambres, Los Bronces, and El Teniente, which formed about 10 to 5 million years ago, it's been suggested that this was related to slab flattening. So there was a distinct period when the subducting slab went from steep, shallowed considerably, and during that shallowing, of course, it generated a lot of compressional tectonics and inversion of the sedimentary basins that are in the zone above the subduction zone. That is regarded as the generation or the tectonic setting, which led to large magma chambers being trapped in the mid-crustal level, eventually releasing the fluids and melts that come up to form Los Pelambres, Los Bronces, and El Teniente in and around these inverted basin structures in the central part of the basin. And as these deposits formed, their formation migrated southwards. So the oldest of the three are in the north, and the youngest, El Teniente, is the south, over about a 5 million year period. And that's probably related to oblique subduction. So we have an environment there that invokes the importance of slab flattening, at least in a continental arc type setting like the Andes. So is that the key? Well, it may be the key there, but does it apply elsewhere? So if we go to a different arc here, this is the arc of the Southwest Pacific, Southeast Asia. Most of what you can see in this picture is actually the country of Indonesia. Australia is poking its nose up in the bottom of the slide there, and in the top in the middle of the diagram here is the southern part of the Philippines. So in that complex arc, and it's a very different setting obviously than South America, we have a very complex series of different subduction zones in different orientations. We've had arc reversal, we've had rotation of different pieces and segments of arcs, and in amongst that there are some porphyry deposits. Those are the green dots shown here in this map that originally comes from Steve Garwin's work a number of years ago now. On the right-hand side, you can see Grasberg, which is a major deposit in Irian Jaya, and in the center of the figure there is Batu Hijau. Both Batu Hijau and Grasberg have been operating for a number of years. Both actually formed at about the same time, about 3.5 million years ago, so relatively young. And then just at the end of last year, we had some excitement with the announcement by Sumbawa Timor Mining, who announced the Onto discovery. So that's down here in the middle of the diagram here. And Onto is a very, very significant discovery. It's been in the works probably for about 5 years, but the major news came out with the announcement of a resource, 1.7 billion tons of 0.89 copper and 0.49 grams per ton gold. So very, very significant deposit. And interestingly, mostly contained with what we would call lithocap style alteration. So in the upper part of what is normally regarded as a porphyry copper deposit. So huge new discovery. So we go a little closer and look at the island of Sumbawa. So this is Sumbawa. So they're not exactly right next door to each other. There's 160 odd kilometers, 170 kilometers between Batu Hijau and Onto, but geographically and tectonically, they're obviously in a very similar position. But Onto is significantly younger. It's probably only about 500,000 years in age, whereas Batu Hijau, as I mentioned, is around 3.7 million years. So a significant given local tectonics difference in age. And if you look at that map, you can immediately get the impression of the tectonic and volcanological setting of Sumbawa. Pretty much everything that you can see is volcanoes and remnants of volcanoes. And in the northern part of the island is Mount Tambara. And Tambara's claim to fame is that it was the largest, potentially one of the largest eruptions in the last 10,000 years, 50 cubic kilometers of magma being ejected from there in 1815, with all sorts of repercussions for the global climate and the people around it. Interesting, the sad fact is that it probably was responsible for the death of 100,000 people. And in the current COVID climate, that's an interesting number. Sadly, we may get there with COVID, but it's interesting that a single geological event can have that kind of impact at a time when the world was considerably less populated than it is now. So with that sobering thought, we'll keep going and think a little bit more now about what other factors we think come into play in terms of the tectonics and porphyry formation. This diagram is from a paper by Jeremy Richards, 2013, who suggested that there's a number of different stages in which porphyries can form, from the subduction through to subduction back arc type environments, collision, and post-subduction, post-collisional settings, and that they have different characteristics in their formation. And then in a very interesting paper that just came out, Mismo Schrader suggested that actually the gold-rich porphyries are forming from deeper magmas and smaller magma chambers, and the efficiency of gold enrichment is what differentiates them. The efficiency of gold precipitation, if you like, differentiates them from the more traditional porphyry copper deposits. So very interesting suggestion that links the tectonic environment to gold enrichment, whether that gold enrichment occurs in alkaline or in calc-alkaline type porphyry deposits. Certainly worth having a look at that paper if you haven't already. So porphyry deposits, as I mentioned, aren't just about the porphyries, and this is another Dixilto diagram, 2010, which is probably one of the most viewed slides in any geological conference in recent history. In this one, the porphyry is the central part of the diagram here, and that could be the copper plus or minus molybdenum gold. But we have a whole range of deposits that occur around the porphyry deposit, around the porphyry core, if you like, including base metals, skarn, replacement carbonate hosted type mineralization, and then a host of different gold deposits at deeper levels and at the very high levels as we get up into the lithocap environment in high sulfidation and intermediate sulfidation styles of mineralization. So the porphyry, although they are the significant style of mineralization in arcs, they come with a lot of others. And of course, there are, as you go around the different arcs around the Circum-Pacific or through the Tethyan, you'll find examples that have more or less of these other types of deposits along with the porphyries. Very few, of course, have all of them. It's only Dixilto's schematic diagram that captures the lot. And lastly, on porphyry deposits, it's really important to remember, and I guess that was really sort of highlighted by the discoveries on Sumbawa and looking at that tectonic setting on Sumbawa, is that porphyries form in very dynamic settings. And nothing is more dynamic than the Lihir gold deposit on the island of Lihir, just off north of New Ireland in Papua New Guinea. And as is now widely recognized, Lihir almost certainly formed following a sector collapse, style of eruption that generated the Mount St. Helens eruption in 1980, and effectively superimposed a shallow epithermal system on top of an actively forming porphyry system. Very dramatic, and this is over here you can see the volcanic edifice in the right-hand corner here, and over on this diagram above it here. It's just virtually at sea level and ejected a lot of material out into the ocean, which has now been mapped on the ocean floor. And so it's interesting then to think about what would have happened and what this would have looked like had it not been just above sea level. What would it look like had it been 500 meters or 1,000 meters beneath sea level, where it easily could have been? And that's my convenient segue into another style of mineralization that's obviously very important in arcs, and that's the seafloor, the seafloor environment of massive sulfides that form massive sulfides. So this is a diagram that comes partly from Sven Petersen, looking at the important hydrothermal vent occurrences in the Tonga-Kermadec arc and into the Lao Basin, going from south to north. And at the south end, of course, is an emergent volcano. This is White Island, which is a famous volcano. Unfortunately, became tragically famous in December last year due to the eruption that caught a number of tourists who were visiting the island at the time, and there was considerable loss of life. So it's a tragic reminder to dynamic volcanic processes. But as we go north, up the arcs and into the Lao Basin, we have a variety of different styles of seafloor vents and so on, which suggests both the presence of magmatic hydrothermal processes on the seafloor or beneath the seafloor, as well as more traditional, what we think of as more traditional black smoker, white smoker type process, reflecting probably largely seawater type circulation. So we see the transition in this arc environment from the emergent volcanoes into the submarine environment, from magmatic hydrothermal processes to more seawater dominated, probably dominated processes, as we go from the true arc into a rifted arc. So there's transition here from that true arc environment into the rifted arc environment. And as we go back then in time and look in the geological past, we can see the evidence for these kinds of things in, for example, Western Canada. So this is a map of Western Canada and Alaska, so Western North America, Northwestern North America. And on this diagram, you can see major porphyry deposits. These are mainly active mines or close to mines in the red dots, red squares, sorry, and the red star in the top top left-hand side of the diagram here is the pebble copper deposit, the most significant in terms of size, but for all sorts of reasons not in production. And then the yellow stars on here are all relatively new occurrences or active projects, so you can get an impression there's a lot of porphyry styles of mineralization through this part of the world. Porphyries conveniently can be divided into two types. There's an earlier type of deposit, which are pre the accretion of the terranes onto the western margin of North America, and they contain, particularly the Cornell and Stikine terranes, contain most of those red squares, most of the active deposits. And then we also have post-accretion deposits that form once a continental arc was established down the western part of northwest North America. And the best example of that is pebble copper at about 90 million years. So it's a post-accretion deposit that formed in the continental arc setting. So if you just keep your eye on that and you sort of look at this area of the diagram here where we can see these different terranes, and then we look at the VMS occurrences in Western North America, you can see we have an equal scatter of VMS deposits as we do porphyry deposits. Most of them, in this case, mined in the past. Not many of them are active in production right now, although there is quite a bit of exploration around some of them. And if you look at the list here, you can see they span a variety of different environments from the continental margin through different types of intraoceanic arc and sedimented ridges and so on, a whole slew of different environments that we would expect to see in arc terranes, current arc terranes, for example, in the complex environment around Southeast Asia and Indonesia. In fact, that complex environment that I showed you before in Southeast Asia is a good guide to the kind of processes that would have led to the amalgamation of terranes and the metallogeny of the terranes that we can see here in Western Canada. Of course, one of the favorites in Western Canada is the Eskay Creek deposit over here, which was discovered in the late 1980s and was subsequently mined and is now closed. And Eskay Creek is special because it has extraordinarily high precious metal content. So the little table on the right tells you 3.9 million ounces came out of Eskay Creek during its 12 or 13 years of operation. And the mineralization there is stratiform, bedded plastic sulfides and sulfur salts, contained within a mudstone unit that sits above a rhyolite. And the rhyolite in this map here, you can see in this diagram, is extensively altered, but the deposit is has a very small footprint at the end of the Eskay Creek anticline. Interestingly, Eskay Creek is only a few kilometers away from the substantial gold-rich porphyry deposits, the KSM suite of porphyry deposits, which are about 15, 20 kilometers to the south, although in fairness, the porphyries are a few million, 5 to 10 million years older than Eskay Creek. But it just again illustrates the complex juxtaposition of metallogenic events in arc terranes. So that was arcs. That was very rapid fire introduction to metallogeny of arcs. And there's a lot, obviously, that I haven't said. So now we'll switch to rifts. And rifts are equally interesting and in some ways more complex in terms of the styles of mineralization that we can see. So here's a list for magmatic nickel-copper sulfides, which are probably preeminent in some respects, in some areas. Enormously important sediment-hosted copper deposits, particularly in the Central African copper belt, but then a variety of other styles of mineralization. Sediment-hosted lead zinc, low sulfidation epithermal, VMS again are very important, unconformity uranium, intrusion-related deposits, a whole host, and there at the bottom of the list again is IOCG CU-AU-U deposits. And those are the question is, do they belong here or do they belong somehow in the arc environment? So rifts, we have a pretty good understanding of rifts. The formation possibly related to hotspots and extension. This is a nice diagram from California State University in Sacramento. And varying extent of extension, varying extent of magmatism, in many cases, generating large igneous provinces. So very huge amounts of magmatism over relatively short periods of time. Rifts may involve initial expansion and then a sag period as they transition from extensive rifting into the formation of a sedimentary basin. And unlike arcs, they then can be extremely long-lived. So hundreds of millions of years is not out of the question as we develop these long-lived sedimentary basin in the rift and post-rift phases. Because of their nature, because they are multiple events with a lot of sedimentary rocks and so on, involving a lot of different fluids, we have potential for a whole host of different deposits related to these different fluids. And of course, the heat flow combined with extension and inversion of the sedimentary basins then enhances circulation and generates the circulation that leads to a lot of these deposits. And finally, of course, in some cases, we have ongoing extension and we end up with an ocean basin forming with associated styles of mineralization. So we'll go initially just to the mid-continent. This is a very spectacular rift, sort of mid to late Proterozoic in age, and generated a host of very important deposits. So in the center of this diagram here, you can see Duluth, which is an enormous resource of nickel and copper. I should really say copper and nickel because it tends to be that dominated. But there are other important examples of magmatic sulfides, including the Eagle deposits that's operating, as well as sedimentary copper at White Pine. Sudbury, which is shown over here on the right, it's nothing to do with the mid-continent rift, but it's obviously a very important magmatic sulfide deposit. And the diagram here on the left again envisages a mantle plume, a hotspot type plume, initiating the rift and the amount of magmatism that was associated with it. So our understanding of magmatic sulfides is really relatively advanced, probably in some ways more advanced than other styles of mineralization, because we can still see most of the components caught in the rock and caught in the act of forming mineralization. That's not to say we understand everything about magmatic sulfides. And when Steve Barnes talks in a few weeks' time, I'm sure he'll tell you a lot more and a lot more of the detail that goes into this process. But the general idea is that the magmas, the melts, or mantle-driven melts that interact with crustal sulfur, assimilate that sulfur, and then the sulfur forms sulfides during sulfide saturation. Those sulfides scavenge metals out of the magmas, and the more magma they see, the more metals they scavenge. So the more physical interaction between sulfides and the magma, the higher the metal content we get. And then the physical concentration processes concentrate the sulfides, and they crystallize, and the nickel sulfides, MSS, crystallize first, and sometime later, at lower temperature, the copper sulfides crystallize through ISS. And because there's a gap there in the temperatures of crystallization, the copper sulfides can in some cases migrate away from the nickel sulfides. So the pictures over on your right, here's a lovely sulfide droplet, which is actually separated between the iron nickel sulfide part of it in the lower part and the copper rich part in the upper part of the droplet here. And that is the upper part from a geological perspective. Some cases the copper gets out along with some of the nickel and iron. And in this case down here, this is the deep copper zones at Sudbury. The copper has escaped almost completely. So it's copper with high values of platinum, palladium, gold, and some minor amounts of nickel. So the copper has basically got away from the nickel. And this begs all sorts of questions about how that process might happen in other environments and how that might lead to the separation between copper and nickel in the rift environment into different settings. Westerman is just an example of a paper that discusses the formation of these deep copper zones. So if we look a little closer here at the Lake Superior in the mid-continent rift, again, I've mentioned the Duluth over here. This is Tamarack, Eagle, which is operating mine. And Coldwell is a very interesting complex. Coldwell is an alkaline, mafic alkaline complex, which has copper-dominant mineralization with some platinum palladium, which shows characteristics of magmatic sulfides, but also shows a very strong hydrothermal overprint or even potentially hydrothermal addition of some metal to that system. And that complexity has been a topic of a lot of controversy over the years. Down here we have White Pine and the sedimentary stratiform copper deposits, and adjacent to that, numerous occurrences of native copper in the basalts through Michigan and in other parts of Lake Superior. So extraordinary amounts of copper. And then on the north shore of Lake Superior, there's some epithermal mineralization and even some unconformity uranium. So in that area that you can see there around Lake Superior, we have many of the ingredients that we expect to find in rift-related metallogeny. So let's go to somewhere that's really known for this. And of course, this is the Zambian DRC Central African copper belt, which produces about a quarter of the world's copper. And so in contrast, porphyries, I should have mentioned, account for about 65–70% of copper. The rest largely comes from the sediment-hosted deposits in the Central Africa copper belt. So these are formed as a series of interconnected basins through about 800 to 600 MA, 880 to 600 MA, and then went through inversion. So there's a lot of complex structure associated with the styles of mineralization in the Central African copper belt. And the mineralization itself occurs in multiple stratigraphic positions at redox boundaries where the oxidized copper-bearing fluids were reduced and precipitated their copper mineralization. This is the endowment. This is a picture. Most of these slides are from Murray Hitzman, and some USGS work when Murray was with the USGS, I think. And this shows the endowment from a couple of years ago, probably, of the major deposits in the Zambian copper belt in the bottom right, and the Congo copper belt in the central part of the diagram. And of course, the big excitement there has been the discovery of Kamoa and Kakula over the last 5 or 10 years. Remarkable concentrations of copper in a part of the belt that was not regarded as prospective. And here's the stratigraphic diagram and section, again illustrating that copper occurs in a number of different places in the sedimentary basin, but again, always at these redox boundaries where the oxidized fluid first meets a serious reductant, usually in the form of sedimentary rocks, shales, and others, and precipitated its copper deposits. So this is a remarkable collection of deposits, and it was put together again by Murray in this diagram here, which again relates to a rift development of a basin and then sedimentation with a significant amount of evaporite formation in the central part of the basin that adds to brines that then can leach metals from the deeper part of the stratigraphic section. Now there is, as I mentioned, considerable complexity in the Central African copper belt, so that the inversion and subsequent deformation, and so there's some controversy around some of the deposits. But regardless of that controversy around exact timing of either deposit formation or remobilization, it's pretty clear that the whole system relates to this rift-type sedimentary basin development. And the components that you can see in this diagram, whether they're exact or not, are the key components that represent the metallogenic setting in a rift in terms of copper, sedimentary copper formation. Okay, so I've done rifts, I've done arcs, and that brings me now to the main purpose of what I wanted to talk about, was to try and see where we place iron oxide copper gold deposits and iron oxide apatite, IOA deposits, in the context of arcs and rifts. So this is a nice diagram that depicts the distribution of the major camps containing significant iron oxide copper gold, and in some cases iron oxide apatite deposits. And as you can see, they're pretty widely scattered on the different continents. They don't line up with any obvious tectonic features, and in large part that's because most of these deposits are mid-Proterozoic in age, so they're captured in the more older Proterozoic terranes and cratons. Although the youngest ones, which I'm going to talk about quite a bit in a moment, the Andean ones down here, are much younger and are part of the subduction-related complex that formed initially on the western margin of South America. So that initially gives you the complexity that we're talking about. If we look at the age range, I've touched on this already, but they're mainly sort of late Archean to mid-Proterozoic, and then we have this younger group in the Andes. They're economically significant for copper gold, but they have a whole suite of other elements with them, which are in some cases of economic interest. There's abundant iron oxides in the iron oxide copper gold, as well as in the iron oxide apatites, and in fact, in some cases, they're mined for iron. So that would be the case of Kiruna up in Sweden, but there's also several active mines in other parts of the world. They are not clearly related to intrusions, although there are intrusions always present in these camps of about the same, if not exactly the same age as mineralization. But there is no clear spatial relationship in the context of a porphyry, for example. But in contrast, there's very strong structural and lithological controls on mineralization, again, somewhat different than typical porphyry deposits. So here is the sort of the mother of all iron oxide copper gold deposits. This is Olympic Dam in South Australia, something that I'm sure many of you are familiar with. Olympic Dam formed about 1590 million years ago, more or less at the same time as the Hildebrandt suite of intrusions. Those are shown in red, and the Gawler Range volcanics shown in the sort of pinkish purplish color. The Gawler Range volcanics are part of a major eruption, large igneous province that was erupted over about 2 million years. So Olympic Dam is amazing. It's 9 billion tons. These are slightly old numbers, so these are approximately 9 billion tons, 0.87 copper, 0.027 U3O8, 0.32 gold, and 1.5 silver. So extraordinary accumulation of metals, and you can see some of the statistics there in the second bullet. 50 cubic kilometers, so that's the same volume as was erupted from Mount Tambora, just by coincidence, containing some of the world's largest concentrations of uranium, copper, gold, etc. We know that there's very strong zoning that's been described by many people, particularly Kathy Ehrig, both laterally and vertically in terms of metals and in terms of copper mineralogy, and that's interpreted by some to reflect a mixing between a deep reduced fluid and a more oxidized superficial fluid. The two samples on the bottom right actually do not come from Olympic Dam, they come from Carapatina, which is just to the south of Olympic Dam, but you can see the breccia textures and the dominance of hematite, and certainly at Olympic Dam, that brecciated hematitic texture passes down into magnetite dominant alteration at depth. So this is a very interesting diagram that came out a couple of years ago, where magnetotelluric data from South Australia was used and demonstrated that there seems to be some kind of deep signature related to Olympic Dam coming down and heading sort of to the north and away from Olympic Dam into this area here. So we're talking down to depths of 60, 70 kilometers into the crust. And the suggestion was made that this conductivity pathway might reflect alteration, hydration, hydrated silicate minerals. The path originally has fluids. It might still contain some fluids. It may contain sulfides. It may contain graphite. Obviously, we don't know, but it is interesting that such a deep, fairly clear feature would be associated with such an enormous deposit. And Roger Skiro in 2018 suggested that this is a post-subduction environment. There was an earlier phase of subduction that more or less had ceased by this time. And so that raises the question as to what kind of remnants are we seeing related to subduction processes, perhaps with superimposed rifting on top of it. So that's the deposit. And now we'll turn to the youngest group of deposits, which is the group of deposits in Chile and Peru. So in Chile and Peru, we have multiple magmatic porphyry belts, and Chile and Peru are best known for their porphyry deposits, again, producing, you know, a good third of the world's copper comes out of this area shown in this map. But the western margin of South America, which is outlined in here in orange, is the so-called coastal belt, which formed from to mid-Jurassic through to late Cretaceous time. And it's dominated by mafic to intermediate volcanism, extensive volcanism, and extensional marine basins that include significant evaporites. The IOCG and IOA deposits are the major deposit type in that belt, and both are mined both for copper, gold, and for iron. But there are also other styles of mineralization, including stratiform or so-called manto styles of copper-silver mineralization, and some porphyry deposits. And the porphyry deposits mainly are late and young, but not exclusively. There are a couple of porphyry deposits that overlap in age, you know, in the Jurassic. So this is the youngest IOCG belt in the world. So we would argue, or Irene Del Real would argue, that this is the easiest place to try and understand them, because if we can't understand them in this environment where they're well exposed and relatively underformed, then how can we attempt to understand the much more complex mid-Proterozoic examples? So we'll zero in on Candelaria Punta del Cobre, which is the central part of the map here, which is a major district containing a number of different iron oxide copper gold deposits. So this is a view of the district, looking over the valley there. The main circle in the background here is the Candelaria deposit, shown in detail on the far left. So the Candelaria has been in production for about almost 20 years now, and probably will be in production for another 20 years. So it's a substantial deposit, mined as an open pit and now going more and more into an underground operation. And many of the other deposits that are shown in the circles here around the district are underground mines. If we go to the next map, and this comes from Irene's PhD and subsequent papers, demonstrating that there are really two major styles of mineralization. There's breccia and replacement mineralization, and that's particularly apparent on the western side of the valley over here, and includes Candelaria, and includes here the deep zone of breccia beneath it, as well as the replacement stratiform or manto styles of mineralization in the upper part of the zone. And in contrast, over on the eastern side of the valley, the mineralization is dominantly structurally controlled, occurs in steep dipping veins and structural features, and that go for significant depth, not extreme depth, but certainly hundreds to about 1,000 meters in vertical extent. The mineralization has been constrained to be about a 115 MA, although it's certainly continued mineralizing process seemed to continue through to about 112. And that overlaps almost exactly with the age of the Copiapó batholith, which is just off on the right-hand side of this diagram here. So about the same age, but there's no evidence that the Copiapó batholith actually generated the mineralization. There is mineralization in the batholith in structurally controlled zones, but there is no equivalent of a porphyry style of alteration that's generating fluids and putting fluids out into the environments in these deposits. So It seems more of a coincidental overlap in age than a progenitor for the mineralization. So if we look at the structural setting, this is a diagram on the right that tries to look at the tectonics for the IOCG deposits in the western part of Chile and southern Peru. And what Jeremy suggested was the period of initial subduction and extension continued and developed and formed the sedimentary basins and so on. And it was when the IOCG deposits were formed. And then we went into contraction and we switched from IOCG deposits to porphyry deposits in the late Cretaceous. And that's certainly, it's consistent with the ages of deposits. However, Rainey's work in Candelaria demonstrated that the mineralization overlaps, it appears, with the inversion of the volcanosedimentary sequence there. So rather than forming in true extension, mineralization seems to be forming as we're in the process of switching from extension into the compression and inversion related to more normal subduction processes. So that raises a lot of questions about, again, are we in a rift environment here? Are we in a subduction environment? And of course, given that we have both sediment-hosted copper in this setting here in Chile, as well as porphyries, you can really argue rift or arc backwards and forwards. And the true answer, of course, is at this point, we don't have a clear picture of what was the key controls. So just to wrap up then, here's a diagram that tries to look and compare porphyry deposits and IOCG deposits in terms of their major features. So there's, as I've said already, significant differences. So if you look at age, porphyry copper deposits are young. And traditionally, less than 100 million years. We've got some good examples that are older, but if you look at the sort of endowment, the majority of the copper endowment is in deposits that are 100 million years or younger. And some of the very best deposits, of course, very, very young, as in Grasberg, Badajoz, Onto, and so on, as I demonstrated earlier. In contrast, IOCG deposits span from the late Archean, arguably through to 2 million years. If El Laco, which is a deposit in the high Andes of iron, an iron deposit, is interpreted as an IOA, it would suggest those processes continue right through to almost the present time. So a very long period of ore formation or ore preservation. Tectonics, the tectonic setting for porphyry is fairly clear, albeit there's lots of complexity in arcs in terms of arc processes, collisions and post-collisional events and so on. But in contrast, we don't have a good handle on where iron oxide copper gold IOA deposits fit into that template. Are they arc related, or is it a post-arc extension, or is it just extension? Could we have rift related IOCG deposits? Scale, porphyry deposits are very large, but they're intrusion centered. IOCGs are probably equally large or larger in terms of district scale alteration, but they're not clearly intrusion centered. At least we don't see the intrusions on which they are centered. Stars mineralization, we understand porphyry stockwork, breccias, and so on, the dramatic release of magmatic fluids, very dynamic processes. In IOCG, we have breccias and so on as well, which are also very dynamic, but we also have a lot of structurally controlled and lithologically controlled styles of mineralization as well. Metal suite overlap, but significant difference in terms of the suite of metals in IOCG. And of course, we also have these very important IOA deposits, which are iron oxide, magmatite, hematite, with apatite, and probably in truth, more actinolite than apatite. So the A probably should stand for actinolite, but there is definitely significant amounts of apatite in these deposits. Zoning, we understand the zoning in porphyries very well, both vertically and laterally. Much more complicated in IOCG. At Olympic Dam, we have beautiful zoning, both vertically, from magmatite to hematite, and in terms of copper mineralogy, out from bornite to chalcopyrite, pyrite, and so on. But we don't have a good handle on how that applies uniformly from deposit to deposit. In fact, one of the characteristics of IOCG is that each deposit has a unique set of characteristics. Touched on zoning, and finally the model. We gain good handle on the porphyry model, not so clear on the components in the IOCG model. We believe strongly that there is a magmatic process that's going on that's generating high temperature magmatic fluids, the magmatic hydrothermal processes, but there's equally clear evidence that surface fluids are involved to some extent, probably derived from evaporites and sedimentary basins. And lastly, I'll just emphasize the temporal setting. So on the top part of this diagram are the porphyry deposits. I mentioned they're young, and as you can see, they do totally sort of gravitate to the very recent, the last 100 million years, whereas the IOCG deposits are spread, and IOA deposits are spread throughout geological time and appear to have some association with major appearance of supercontinent assembly. Whereas porphyry deposits, partly because we don't see ancient examples, we don't see those kind of relationships. Now, of course, the big question here is this timing here of porphyries related to their formation or just preservation? And many would argue that it's a preservation, remembering that porphyry deposits form in this dynamic environment. Think of Sumbawa, the island of Sumbawa, or think of Lahire, where preservation potential is going to be very low, compared to IOAs, which if they form in more extensional environments, are likely to have much greater preservation potential. So to wrap up, so we have arcs and rifts with contrasting metallogenic environments. The preservation potential is higher in rifts, clearly, because you're downdropping and you're having sedimentary basins that form over long periods of time, compared to arcs, which are forming in dynamic, tectonic, and volcanological settings. And hence, porphyry deposits are young. I said here less than 200, but less than 100, as I said earlier, for the majority of the endowment. In IOCG, we have evidence for arc subduction and rift extension in the mid-Proterozoic potentially, and then certainly in the younger deposits in the Mesozoic. And so we have potentially a mixed setting or transitional setting that may have components of arc metallogeny and rift extensional sedimentary basin metallogeny. In terms of the Andean, the setting there includes these different styles of mineralization and seems to be a transition between a true extensional setting, albeit probably arc-related or subduction-related, into a more continental arc, shallow subduction, and the formation of the porphyry copper belts in Chile and Peru, for which the area is really, of course, most famous. And I'm just going to leave you now with one last slide, hopefully just to provoke a bit of conversation and discussion, is what about the metals and the fluids? So in arcs, we have a subduction, supersubduction zone type melting going on, and that's where we think obviously a lot of the metals and fluids were generated, whether they came from the actual subduction zone itself or from that environment above the subduction zone, albeit there is interaction with other fluids as we get into the near surface, and they can be brines, seawater, meteoric water, etc., and some component of rock, leached rock, may play into some of the styles of mineralization that are found in those environments. But dominantly, we're thinking magmatic, subduction-related magmatism and magmatic hydrothermal processes. We go to the rifts, we have mantle-related magmas and metals, but we require crustal sulfur. And of course, that's convenient in sedimentary basins, because sedimentary basins have lots of potential both for reduced and oxidized sulfur, sulfate in those settings. So it's a good place to find that sulfur and get if the magmas can interact with those rocks. And then we have basin fluids and their role of evaporites, seawater in many settings, forming volcanic and sedimentary hosted styles of mineralization. And that leaves us again with our enigma, the IOCG enigma, the hybrids. They seem to have a mantle signature. There's good evidence for mantle magmatism and mantle components within the fluids, but there is also crustal components and potentially, yes, maybe basinal fluids that are involved in these deposits as well. And clearly, the question marks that are littered through that final bullet are probably the takeaway, is that there's a lot still that we don't understand with IOCG deposits. So I'll leave it there and take some questions.